Welcome to the session 10A, electronic measurements. I hope you managed to sleep well last night because we have a very interesting morning ahead. So we have 6 speakers ahead, and I'm going to chair the session today. My name is Tomas. I'm from Spain, and you know that you have 15 minutes for presentation and Q&A. So we'll keep the presentation to 12-13 minutes, and after that time I'll make you know that your time is almost running out, so we have time for questions. So our first speaker is Shu. Sorry. And she's presenting a work entitled Wireless Feeding Rate Real-Time Monitoring System of Combined Harvester. Okay, thank you.
Thank you, Chairman, and good morning, everyone. It's my great pleasure to be here to do the presentation. The topic of my presentation is wireless feeding rate monitoring system of combined harvester. So firstly, let me do some brief introduction of combined harvester. It is a multi-function machine which can be efficiently used into harvest the grain crop. And the process has some problem. In a moment, sorry. Maybe we can see outside. Yeah. For this machine, it has a lot of different process for producing the grain. This is the header of the combined harvester, and this part is the transport, and this is the threshing drum. The grain will be separated from this part with the straw, and for the bottom of this, it's a clean processing. After the clean processing with this part, it will collect the grain into the storage part. So this is the main purpose of the combined harvester. Okay. And for our work is to test the feeding rate, because the feeding rate is one of key operating parameters of combined harvester. The working speed and power consumption of combined harvester is depend on these parameters. It is very useful parameters for the driver to control the working speed of the combined harvester. In the past, there have two typical ways to test these parameters. One is to test the pressure of transportation bottom plate for this part, the transportation part, and another method is to test the torque of the threshing drum. For this is also in the past is very popular, but nowadays the combined harvester is use hydraulic system. So for this part and this part, they use a hydraulic system to control it. So it's difficult it don't have some sprocket. So sprocket way. So we can't use both of this method. So we try to test this part, the header, because the header also use sprocket wheel. So we will test the torque and the speed, the rotation speed of this part to get the feed rate of the combined harvester. So in our work, this is a picture of the header, and this part is auger propeller. This part is auger propeller. You can see this part. It's this part, yeah, inside. And in our research, we will install the sensors in the front of the combine harvester to get the speed and the torque parameters of this harvester. And we also developed the sensors and detecting system by ourselves. This is the picture of this. First of all, we have to get some mathematical model. So we, according the working principle of Auger propeller, we get the relationship between the feeding rate and torque and rotation speed with these equations. After that, we have to, for this part, rotation speed is not difficult to test. Only with Hall sensor is okay. But for the torque, we developed the sensors by ourselves. As the spoker wheel has enough lateral resistance force, so we refit this part, the sprocket wheel, and it looks like this to make it as an elastic element, and we paste the strain gauge into this part, and to build a bridge circuit. So this is the picture of our detection system, and with this system it has 3 parts. One part is the power supply, it's very important, and another one is the bridge circuit and the signal conditioning circuit for this part, and this is our refit sprocket wheel inside. All for the torque signal, it will transmit by the Zigbee module. In the Zigbee module, we also apply. This is also we apply by ourselves because of our relay request. And in this part, it includes the amplification and filter, AD conversion, and the Zigbee transmission module in this part. After the development of these sensors, we do some laboratory calibration, and we get the voltage, the relationship between the voltage output and the torque. With this is a laboratory picture. And we also do the fire test in 2015 at Henan province. It's in the middle of China. This is the picture which we do the fire test. And you can see for this part, we install our sensors, detection system like this. This is for torque, and this is for speed. Speed is only if we use the Hall sensor is okay. And from this part is the testing flow chart, how to work. The fire test separated by 2 parts. One part is the celebration part. So for this part, we will do some exam to make sure the coefficient K and the coefficient F of this test. And after this, we will do the real fire test. This is the result. We choose 8 group. We totally we did 25 group. We choose 8 of them. With the analysis of all the results, the error range is between 0.55% to 6.68%, and the maximum tax error is not exceeding 10%. So for us, it's okay. For the combine harvester, it's okay. It's not very high. So the conclusions. In this paper, we develop a new wireless detection method of feeding rate based on torque measurement of auger propeller is described. And our system includes two parts, two main parts. The strain gauge to measure torque of real-time harvesting feeding rate, and the wireless module which can be transmit the signal to our data acquisition system. And with the laboratory calibration and fair test, our system was verified. Okay, thank you.
Okay, we have time for a few questions. No?
Maybe just small recommendation. When you put the number of errors and you use 3 figures, it is maybe too much, because error is already shows that the level of confidence is so low that you should use maximum 2 digits in your error description. So just recommendation. So smaller recommendation.
Okay, thank you.
Thank you.
Thank you.
I have one question.
Please.
What is the frequency that you need to sample your feeding rate?
It's not very high. We will only set it 1 second. It's okay, not too high.
Oh, okay.
Yeah, because the speed of a combine harvester is also not too high. Almost 4 kilometers per hour, the highest.
Okay.
Yeah.
And what is the stuff that you are harvesting?
Yeah.
What are you harvesting? Is wheat or?
It depends the weight, grain and the corn. Now we also do a lot of work for the corn, harvesting corn. Yeah.
No more questions? Yes, I have another one.
Thank you.
And what is the use of this data that you get? If the feeding rate is too large or too low, what do you do then?
We use it for sometimes it will show for the driver. And if the feeding rate is too high, they will decrease the speed. Yes, because the tracing drum is very easy to broken. If it's feed in too much. So firstly, it's for the driver. Another is for our automation control system. With these parameters, we can do some automation system to control the different key components of the harvester. So it will not have some problem when it's working.
Okay.
Yeah.
Okay, thank you very much again.
Thank you.
And now we can go to our second speaker, and this.
Wait a minute.
This is a work into the metrological properties of a two-output transducer for measuring sum and difference of small resistance, and it's presented by Adam Michkowski.
Yes, Adam Michkowski.
Thank you.
Thank you. Ladies and gentlemen, it is a group work of 4 authors from different departments. And my work will be connected also with a strain gauge, like Xin talked something about strain gauge. My transducer also can be used for measuring strain. And this work is about this is a continuation of previous works on transducers we've made with my colleagues, and we usually made some articles about Whetstone bridge, Anderson loop, comparison of these circuits. We also tested current sources, thermal effects, and some unsteady states when switching over the current sources. And this will be to present a prototype of converter transducer. two output, two input, to measure small changes in resistance, to show some technical problems in realization because current source is pulsed and it caused some problems, technical problems. The circuit is more complicated, and yes, and of course to present some results, some parameters like nonlinearity error, sensitivity, resolution, maximal frequency of work, settling time, and so on, so on. So what do we measure? Firstly, we measure little changes in resistance in this range. I mean, we measure sum of two changes in resistance and the difference of two changes in resistance. It can be strain gauges, two strain gauges, and as you can see, this difference can be positive and or can be negative also, because the range is plus minus 1 and plus minus 2 in fact. And the idea of this is to convert the changes of resistance into analog voltage and then into digital form by using of with the use of measurement card, national instruments with parameters like this. And in this test I used two precision resistance decade boxes, not real sensors. Real sensors will be used in the future, but because of the reason is just resistance decade boxes, not are linear. And this is the scheme of preconditioning module. Here we have the sensors. This is 4-arm bridge. Here we have electronic keys like this. It's MOSFETs, and yes, and we used current source LT3092, but we also tested another current sources, and this presentation was on Monday about other current sources which can be used in this project. And the idea is to switch on and switch off the transistor keys, yes, and to measure two voltages on the diagonals of this bridge. And as you can see, the keys are quite fast. Rising time is in nanoseconds, falling rising time is in nanoseconds, and resistance of these switches are 1 milliohm, so it cannot influence on the resistance in arm bridges. This is control and output signals, control signals, output signals. The idea is to measure average of UDC1, UDC2, UAB1 and UAB2, but there is some problems. This is bipolar square wave, quite high amplitude, and just a little part of useful signal. So, and of course, this voltage depends on the difference and sum of resistances. So we should make a proper signal conditioning circuit. And this is just the first part, which is to create reference voltage, to convert differential voltage into single-ended voltage, and to give it to the input of amplifiers, in fact, to amplifiers here. And these voltages from the diagonals of the bridge are amplified, firstly by differential amplifiers, and then by instrumental amplifiers, and gain is in this range. What is for generally this complicated, maybe complicated circuit? It is just for giving zero voltages on the output when the increment changes in resistance are zero. And if we do this, the gain can be higher and the resolution can be bigger. And but it is not so, how to say, ideal, because if we have a current source, and current source it is switched, we have unsteady states, and amplifiers get in saturation state, and it takes time, of course. Amplifiers are saturated 120 microseconds, and fall time is longer, is 300 microseconds. So in fact, if you sum up, it is about 500 microseconds. So we should wait that time and then give it to a DC converter, for example. So this is a timing diagram, and that's why, because of these unsteady states and situation and so on, we introduced a time delay. I mean, a DC converter waits 1 millisecond and then sampling and convert the signal. And that is a practical realization in DIN rail box. This module consists of power supply, because we need a bipolar supply for amplifiers, for example. So we have a DC-DC converter here, and this is this metrological part, these two channels, potmeters, amplifiers, and so on, output, inputs, and what about the results? These results were made in different situations where two resistances were increased or decreased, one increased, one decreased sometimes. And by analyzing all these situations, cases, maximal error, maximal difference, nonlinearity error was about 0.08 ohms. Relative, it is less than 5%. Resolution, sensitivity. Resolution is 0.001 ohm, and sensitivity is 1.5 ohm, volt for ohm, divided by ohm. And the big problem was noise filtering. We used, I didn't show on slide filter because I placed a simplified circuit, but we used low-pass filters between output of bridge and first amplifier and that reduced noise from this value to this value. Yes, maybe 4 times. 4 times. This is a noise in peak-to-peak values. Yes, peak-to-peak values, and so we used also shielding. We shielded all the circuit by cables, and this reduced slightly also this peak-to-peak noise. So we needed finally to make software averaging of these results, and then the noise is very, very good. It's 2 millivolts peak-to-peak, and can be used. The signals can be used, and it is thermal tests. This is, I think, one of the hardest things in all of this, because the module self-heated because of this DC to DC converters, power supply, and about 10 Celsius. So we need to wait 10 minutes for warming up, and then if it is in steady state, when temperature is steady, we also measure drift, zero drift of bridge, and this zero bridge was quite good. It was 0.25% of range. To summarize this all, yes, in this table you can see the parameters of this transducer. We also checked settling time during two resistance change 1.01 ohm. It was 15 milliseconds. What I can say, it is quite complicated construction, because we have here bipolar supply, this switched current source. Not every current source is useful to this project because of its dynamic parameters. And yes, this maximal frequency of switching is limited by unsteady state of output voltages, and of course using DC current source or DC voltage source, probably the circuit is much easier, but the results also. Thank you for attention.
Thank you very much. So we have time for a couple of questions.
When I look on your, thank you for your presentation. When I look on the noises, because maybe this is something what could be very interesting, I see like two components, frequency components. Have you made any analysis of the sources of this noise and what is the spectrum? Because it looks quite deterministic in some way.
Yes, I think it is radio frequency noise, of course, and it is low frequency noise in general. And we even add we made such a box from Caprum and added on the top of this PCB and shielded it also, because yes, many random noise influence of
location.
Yes, electromagnetical interference, radio frequency interference, because the changes we measure very low. Yes, so all of it has influence.
But at least in this picture that you show, seems to be that there are two main components of the frequencies, so maybe it was
Maybe.
interesting to analyze which peaks
Uh-huh.
of the frequency you could get in
I
this noise.
didn't do that deep, but I tried to just to limit, just to limit. Used filter, then shielding, then software averaging. It's also filtering, yes. Yes.
Do you expect some nonlinear behavior from real sensors?
Yes, I think because if we have, for example, strain gauges, we glue it to any surface, and there is some nonlinearity caused by this. If we stretch and compress, that's why I used the cut boxes, because I would have nonlinearity of sensor and nonlinearity of circuit, and I would not make any conclusions.
And do you think you can cope with this nonlinearity with this device?
Yes, probably. Maybe this. Usually, if we have in classic metrology, yes, we have Whetstone bridge and quarter bridge, for example, half bridge, and sometimes we can compensate nonlinearity of sensor with nonlinearity of circuit, yes, and this final, how to say, final line is more linear.
Okay, we can thank the speaker again. Thank you very much.
Thank you.
Our next speaker is Stu. Momsilo. Yeah. Okay. And he's presenting a work entitled An Empirical Methodology for Power Analysis of CMOS Integrated Circuits. Okay.
So, good morning, everyone. My name is Momčilo Krunić, and I'm coming from the RTRK company from Novi Sad, Serbia. Today, I would like to present my research titled An Empirical Methodology for Power Analysis of CMOS Integrated Circuits. So, the most interesting aspect of this research is that provides the direct link between the highest level of abstraction, such as instruction, back to the lowest level, such as CMOS transistor. Context of this research is embedded processors, software development tools, and all that integrated into the integrated development environment based on Eclipse RCP. Used for programming target platform. And this is one of the views from the IDE that inspired this research. You can see that it shows a core activity graph during firmware execution. So the main question was that inspired this research: can we extend this view in order to provide information about the energy that is being consumed during firmware execution? So, in order to answer that question, we have to decompose energy dissipation to base components, and those are static energy dissipation and dynamic energy dissipation. And dynamic energy dissipation can be from active peripherals or DSP cores, and DSP cores dissipate energy while running in idle state or executing instructions. And if instructions are being executed, we can divide base costs and inter-instruction effects. I won't go to details in those components. That is not the focus of this presentation, but I just want to emphasize that those are the base components, so everyone should be aware of. So this is this slide shows how energy is related to the size of a process node. You can see that decreasing the size of process node, actually we are increasing dynamic and static power that are being dissipated. Actually static power even more than dynamic. From the table we can see that on a 19 nanometer process node, when we decrease process node to 45 nanometers, dynamic power per square centimeter is increased twice, and static power is increased 6.5 times. So meaning that decreasing the process node, static power becomes the dominant component of dissipation. This slide shows energy dissipation during one clock cycle, and we can see that surface of blue rectangle represents dynamic energy consumption, and you can see that this surface is constant over the time, meaning that dynamic energy dissipation is constant. It does not depend on clock cycle. On the other hand, we can see static energy consumption, which is red surface. We can see that static power dissipation is constant over the time, which is actually the height of that red rectangle. Those are some main properties of those components, which will be used further on during experiments. So on this slide we can see just the main components of leakage current represented on CMOS inverter. There are actually 4 components that building leakage current, which is the main reason for static dissipation. And we can define leakage current of CMOS integrated circuits as sum of leakage currents of each individual CMOS transistor that is under the voltage supply, and therefore we can also define static power dissipation as well as energy that is being dissipated during one clock cycle. Also we can define, we can see that dynamic dissipation is created when we have changed input state of the CMOS transistor, and we can define that dissipation as a multiplication of equivalent capacitance, which is being charged and discharged during those changes, and voltage supply on square and frequency. So we can define dynamic dissipation as a sum of all of each individual dynamic dissipation of CMOS transistors, and this is the most important contribution of this dissipation. You can see that is a sum of each individual equivalent capacitance, and we can define that as effective capacitance, which means that is the actual capacitance that's being charged and discharged during one clock cycle, and that can be used as a quantitative measure of energy, dynamic energy dissipation. So in order to identify which is the dynamic and which is static dissipation, we can use properties of those dissipation that I have mentioned on the graph that have red and blue surfaces. So we know that static dissipation does not depend on time, on period of clock cycle, so we can use that property in order to identify leakage current. So based on that based on that property, we can create two equations in order to identify which is the part that does not depend on clock frequency. So we have one equation and the other. So we are actually performing measurements on different clock cycles, and then we are calculating leakage current. And this is the outcome of that experiment, and you can see that relative standard deviation is around 0.5%, which means that we obtain pretty reliable data. On this graph, we can see the energy actually power dissipation. That is power, not energy. So the blue rectangle represents the overall power dissipation, the red one represents dynamic power dissipation, and the green one is the static dissipation. You can see that on different clock cycles the static energy dissipation remains the same, but dynamic dissipation is decreased, because when you decrease the clock frequency, you decrease switching of activity on CMOS integrated circuits, so that is expected behavior. So on the other hand, if we observe energy that is being dissipated during one cycle, we can see that that dynamic energy dissipation is constant over the time, but static dissipation is increased as we decreased or we increased the clock period. So that is also expected behavior. So based on those two graphs, we can make two conclusions: that when core is in idle state, the frequency should be clock frequency should be decreased as much as possible in order to reduce switching activity, therefore dynamic energy dissipation. And on the other hand, when core is in execution mode, while executing instructions, frequency should be increased as much as possible in order to reduce static energy dissipation. And this is a table of 5 cores that we have on our target platform, and effective capacitance that we calculated. So this is, for example, effective capacitance of microcontroller while running in idle state, meaning that this is the actual capacitance that is being charged and discharged during idle state of microcontroller. And we can make some conclusions based on this. This can be very valuable for firmware developments when we make instruction set energy characterization, meaning that each individual instruction is tagged with its own energy dissipation. Also, inter-instruction effect could influence instructions scheduling during firmware development. Very also significant could be power-aware compiling, meaning that the compiler as a tool could use those empirical data in order to generate more efficient, energy-efficient code. And firmware developers will have feedback about firmware application energy consumption, meaning that they can maybe create more energy-efficient firmware solutions. And also various tools could be developed to make some hints to developers in order to make a more energy-efficient firmware solution. Thank you very much, and if you have any questions, I will be glad to answer.
Okay, we have time for a few questions.
Yep.
I have one. When you separate dynamic power consumption and static, then it could be probably that dynamic consumption depends also on temperature, and when
Yeah.
it influences the static consumption. And did you consider this?
We actually didn't consider that kind of influence on this research, but maybe that could be interesting in the future experiments. But we didn't have that kind of observation during this research.
Okay.
Yep.
You title your presentation analysis, but I think that the final, let's say, outcome of this research should be some kind of heuristic model, because you search for some pattern in the behavior.
Yeah.
So what you show as the results, I think that is possible to find some, let's say, equation or let's say model as the final, because this measurement, I can see already from this that it's possible to in some way
That is, yeah.
find some pattern. So I would recommend you to summarize it as equation dependent on frequency or some others.
That is quite correct. This is actually just a part of my PhD dissertation. So the whole research contains those equations. So like dependent on effective capacitance, frequency, and voltage supply. So equation evaluates power and energy consumption during firmware execution. So that is like the final outcome of this research.
Because analysis is not the goal.
Yeah.
The goal is the modeling.
Yeah,
So,
yeah.
so let's say this is the tool to find the pattern.
Yeah, and this is this measurement that I have shown here. It's I have wrote a patent for that also in Serbia. So that is kind of part of the whole picture, and not the whole, but I have those equations that evaluates energy consumption.
Thank you.
Okay.
Thank you.
Okay, thank you very much. Okay, our next speaker is A. Riedel, and he's presenting a work entitled Comparative Measurement of Cardiac Cycle by Means of Different Sensors. Okay, good. Welcome.
Hello, my name is Heiko Priidel. I'm a PhD student from Tallinn Technical University, and I'm presenting part of my PhD research work, which is actually related to detecting hematomas and cancerous areas from human brain. So a few words about the motivation of my work, about ultra-wideband radar working principle, which is a main device and method for detection of the tumors in the brain, and problems related to that kind of measurement, and then about multi-sensor measurement device, which is designed to understand actually ultra-wideband radar signal sources, and a few words about current results. So ultra-wideband signals for medical diagnostics are under development already quite a long time, over 10 years. And recent developments in component base allows to actually implement them also in real hardware. There are numerous studies about signal sources of ultra-wideband radar device, and there is still dispute about where actually signal is originated from. Some research group claiming that signal actually is coming from surface of the patient skin, and another opinion is that signal is originated from the internal organs or tissue layers. But there is no clear understanding about real situation. So a few words about ultra-wideband signals and radars. Conventional radars are using continuous wave, like CW radars or Doppler radars, generating a carrier. And reflection from the object will be then detected and analyzed. Ultra-wideband radar works in a different way. Instead of generating a carrier, we are generating single impulse, as short as possible, and generating that kind of impulse typically in a range of tens of picoseconds up to hundreds of picoseconds, is leading to spreading impulse energy to a very wide frequency range. Allowed range for ultra-wideband radars is 3 gigahertz up to 10 gigahertz, so all the energy is actually spread on a very wide frequency range. And receiving the signal is actually working in a time gating receiver principle, that we are generating impulse. This energy is transmitted through the antenna towards to the object. Part of the signal will be reflected back, and here we have a correlation receiver which is capable of actually detecting signal very precisely in a spatial dimension. So we can detect actually area where the signal is coming from. And reflection from the object is happening because of the electrical properties of the different tissues. So part of the signal will be reflected back in a tissue layer boundaries. So in case of measuring, for example, heartbeat signal, when we are transmitting energy, we will get first reflection from the air skin boundary, second reflection from the fat muscle, and finally some reflections from the heart. And because of heart is moving, we can detect signals. Unfortunately, signals are attenuated very much. For example, 10 gigahertz signal will be attenuated over 200 decibels or even more. So there is questionable if we really can detect signals from the heart wall. From this graph, you can see that different reflections from different tissue layers, skin, fat, muscle, cartilage, lung, and finally from the heart and blood layer. So this signal is attenuated like 10 minus 100 decibels. And what kind of this radar is detecting, what kind of signal it's detecting. So we can see this phase breathing was hold, so we can see only a heartbeat signal, and there is following one deep breath cycle where we can see also basically moving of the chest, and then on top of that heartbeat signal. Now, where those signals are actually originated. Heart movement is a main source, of course. Sorry. And now we have several possibilities why we actually get that signal back. One possibility is blood perfusion on the skin, because of amount of blood is changing in the skin. reflection coefficient is changing, might be also antenna coupling changing, and this will generate the signal. Another possibility is inside body organ movement, which will lead to skin movement. So there is possibility that we actually not measuring the heart itself, but moving of the chest, which means that that is purely mechanical movement. And then echoes from internal organs, antenna coupling, far field, near field coupling, black body radiation, and sources like that. So there is probably many possibilities, but where the signal is really coming from is still not 100% clear. So part of my research, I developed a small device to measure actually how much possibly signal is coming from movement of the chest or from the blood perfusion from the skin. So this device was attached to the body with a standard EEG electrode attachment, and we measured the heart aortic valve acoustic signal, movement of the skin in means of acceleration sensor, and optically we measured also amount of the blood in the skin in the means of reflection coefficient of the skin itself, which is basically a reflectivity test in IR and red light range. Measurement setup was set up like patient was sitting in a chair. We had ultra-wideband radar transmitted signal and measured it through the national instrument ACU card. Then we had a multisensory measurement device which measured the acoustic signal, skin perfusion, and chest displacement of movement, which will also lead to the duct card. And for a reference, we measured the ECG signal, and so main goal was to put all these signals to the same timeline, so that we can compare actually radar output signal with physiological processes, and possibly compare it with multisensory measurement signals to verify how phases are shifted that related to heart movement or skin perfusion signal, how radar output signal is actually changing, and is there any correlation between them. So few signals are still, this process is ongoing, few signals are still not measured, and then this device will be developed further. Also analysis is not finally yet done, but if you look radar output signal compared to the ECG signal, we can see radar minimum, radar signal minimums exactly the same time as ECG signal is appearing. And if we look now radar output signal or chest displacement signal compared to ECG, then we can see that chest displacement actually is not in the same time as ECG, so, and not at the same time with a radar output, which can show that signal source is coming somewhere else. There might be some part of signal from actually chest movement, but there is still possibility that part of the signal coming from the deeper layers. And another interesting result was blood perfusion signal, and actually the signal change is very low. It's less than 0.1%, which showed that the probable source, skin perfusion as probable, blood perfusion as probable source for the radar signal is also unlikely. That which also supports the idea that the signal is still coming from internal layers. For conclusion, this multisensory device was developed, and the preliminary tests and experiments were conducted. Results showed that probably signal source is not only the skin movement or body or chest displacement signal, but we have to analyze it further. One idea is to actually mechanically restrict chest movement and try to measure radar signal this way that chest can't move. And we have also idea to add bioimpedance measurement channel here to also correlate signals with bioimpedance measurements. Thank you.
Thank you very much. We run out of time, but there is one short question.
About UV ladder, did you buy some solution or you make it by yourself?
This was our own development.
Yes, okay. Thank you.
Okay, thank you very much. Our next speaker, Wojciech Oliva. Yes. And he's presenting a work entitled Fast and Accurate Frequency Meter using the interpolated DFT method.
Oh, good. I check it when I load it. I don't know. Sorry. I'm not used to
No,
this.
the one to the right, the one you have tried just to the right. Yes, this one.
Oh, okay. Thank you. I've done it with a very old version of PowerPoint, and I'm not used to the newer one. Okay. Sorry for that delay. I want to show you my and my colleagues' work on the frequency method that uses interpolated DFT method. First, I remind you or introduce you interpolated DFT method. If using only discrete spectrum obtained after making DFT to estimate frequency has a very poor resolution. Simply, it is only the index of the maximum point of the spectral line. But, as you can see, the shape of the spectral line have still have information about the true frequency of the signal. And interpolated DFT methods, because there are many of them, simply use two or more greatest points to calculate that displacement from nearest integer. Some years ago I introduced my own version of interpolated DFT method, and it is so simple that you can see all of it on that one slide. It uses two maximum points. It depends when it is point with index L, and L plus 1 is bigger than which is bigger, L plus 1 and or L minus 1. So it has two versions, but they are very, very similar. It is quite amazing that these simple equations could lead to estimation of frequency with very high precision. If we define the method gain as how many times the estimation frequency is better than using only discrete spectrum, then this gain could be either hundreds of thousands. And after some articles that I have written, in which I analytically do some analytical assumption about properties of the method and make some simulations, the question arises if these properties will occur in real environment and reality. So we decided to, with my colleague, to build as fast and as accurate and as simple frequency meter as we could. We choose 32 bits Atmel microcontroller with DSP and floating point units inside, external fast 14 bits analog to digital converter and some other elements. And the prototype was built. To check the properties of the device, we use signal generator Fluke 6080A, which produce very stable and spectrally pure signal. The measurement procedure wasn't so simple that let me introduce some terminology. First, device acquires series of samples, voltage series of samples. Then FFT is made, digital spectrum is obtained. After using interpolated DFT method, the frequency is estimated, and many such estimations forms a set of frequency measurements. So we have two different samples, voltage and frequencies, and two different series, but first I will call always series, and the last I try to not forget to name only set of frequency measurements. First, let me show you the most basic properties of the matter. Simply, steady signal with frequency 1 megahertz was coupled to the input of device, and this is set of frequency measurement. Very normal look. Histogram of that set is shown here. It has the shape which is similar to Gauss. This was done for the FFT size 1 kilosamples. I didn't tell it, so I come back here. FFT size is the number of samples in voltage series. Sorry. On the next slides, the only thing that is changes it is FFT size. For bigger FFT size, we have the signal with lower noise, and the histogram is more narrow. The same is for 4 kilosamples in FFT size 4 kilosamples. I have had to change the scale because it will look like a clear line almost. And the last one, FFT size equal to 8 kilosamples. And histogram consists almost only of four elements. Let's summarize these main properties of the matter. As could be expected, the best estimation was achieved for the greatest FFT size, and in contrary, the highest rate of frequency measurements was achieved for the smallest FFT size. But there is one more interesting result. It is method gain for 4 kilosamples, which is bigger than for 8 kilosamples. Let me explain it one slide later. First, I want to show you the influence of noise on accuracy of frequency measurement. It is well known that estimation of parameters of signal that is influenced by noise has some limit, that it is known as Kramer-Rao lower bound. For in situation when none of three sinusoidal signal parameters are unknown, the limit of such estimation of frequency is given by this equation. Sometimes ago I derived the equation, the limit, for my own version of interpolated DFT method. Both relations are drawn on this picture. There is drawn also measured values, and something strange happens here also, because for signal to noise ratio greater than about 25 decibels, the accuracy do not increases with increasing SNR. That two strange observations led us to suspicion that we have problem with using mathematics, with using single precision floating point format. And indeed, if we look more carefully in some histogram, it could be seen that the difference between neighboring points has only two values, which is one time and second time by the smallest one. we of course were aware that single precision floating point format has a limitation, but I must honestly say that it was for me something surprising that we achieved the delimitation as easily. Let's look at other sources of errors of interpolated DFT method. The stability of or instability of input signal is such source of error. When we try to model the variation of input signal amplitude during acquiring process, it could be done in the simplest way by using amplitude modulation. In such case, the systematic error depends on modulation index. On this figure it was 0.4, modulation frequency, and the modulation phase. It could be seen that the greatest systematic error occurs in this region. So we choose to try our device in such condition that we cutting this feeder on this region, and the comparison between analytical predictions and measured values are shown on these pictures. The last influence on accuracy of frequency measurement was frequency variation itself on when the samples are acquired. But it could be easily seen that if we have sampling frequency, it behaves like sampling anything else, and it must obey Shannon-Nyquist theory. So if we have a small rate of changes of frequency, we simply see it in set of measurements. When we
should jump to conclusion.
Okay, it was only one. So our method was fast and accurate. We find new limit caused by using a single precision floating point, and that's all. Thank you.
Okay. Okay, we are already on the time of our next speaker, so I think it is not fair for him. So if you have any question, you can ask him later, I think. Yes, okay. So thank you very much. So this is our last speaker. He is Margus Metzheim, and he's presenting a work about realization and evaluation of the device for measuring the impedance of human body for detecting the respiratory and heart rate. Okay.
Thank you, Mr. Chairman, ladies and gentlemen. My name is Margus Metzheim, and I'm a BSc student at Tomas Department of Electronics at Tallinna University of Technology. Today I will speak about my work in the field of measurements of electrical bioimpedance and present a device for monitoring the cardiac and respiratory activity. The title of the presentation is the realization and evaluation of the device for measuring the impedance of human body for detecting the cardiac and the respiratory activity. Firstly, a short introduction. Outline. Firstly, introduction, and then the idea and realization of the device. Then shortly about the methods and measurement setup. Then I'll share the results with you with the focus of breathing and heart beating, monitoring these processes. Then shortly the conclusions and show you a bit of my future plans. Okay, introduction. The monitoring of vital signs has become an important topic in personal healthcare. The reasons are the popularity of smartphones and its accessories. This has happened through the development of technology and the interest to personal health. To gain access to these processes, there are a variety of methods available, from which in current presentation the electrical bioimpedance is used. Electrical bioimpedance, or EBI, is a tool that is used to describe the properties of biological organisms. And it is done in a way that an electrical stimulation is applied to the object and its response is monitored. The fact that the processes of breathing and heart beating are variable makes it possible to follow this inhalation and exhalation and pulsating blood in the organism. The choice of the method is one side of the coin. Another side is the development of capable devices able to monitor the vital signs in real time. What is the key issue in developing the wearable devices is the contact interface with human body. Traditionally, in personal heart rate monitors, the direct contact is used. This presumes the direct contact of the electrode to the skin surface, and this is not always visible and not always comfortable. Then the capacitive connection proposes an alternative. Nevertheless, proposing new problems and issues, mostly in the fact that there will be a motion artifact. In today's presentation, the idea and evaluation of a custom-made measurement device for monitoring the cardiac and respiratory activity is presented. So firstly, the idea of the device is to apply a certain signal onto the object and measure the real part of the total impedance in two electrode configuration. The excitation signal is generated by oscillatory chip. It is a square wave signal of adjustable frequency. After the measured signal, the object is passed through inverting amplifier and is synchronously switched. After that, it is integrated and bandpass filtered. And for making it visually available on the screen of oscilloscope, it is amplified and low pass filtered. Here is the picture of the device and the method and the setup. Measurements were carried out to evaluate implemented measurement device for monitoring the vital signs, breathing and heart beating. We used a single volunteer and dynamic bioimpedance reference device designed in our institute. We used 3 different electrodes, traditional ECG electrodes, large foil surface plate electrodes, and textile electrodes of stainless steel with stainless steel yarn. And excitation signals above 2 MHz were used to focus on the capacitive connection. So firstly, the results of the measurements on this dynamic bioimpedance reference. This device enables to adjust imitated variable impedance of human to adjust the parameters of respiration and heart beating. It was directly connected to the implemented measurement device, And it can be seen that in the cases of 5 megahertz and 20 megahertz, the result is the amplitude of breathing is most clearly detectable. Secondly, the ECG electrodes, they were positioned on the body to cover the full trunk. That's it, yeah. And it can be seen that breathing is available. Cardiac activity cannot be seen from this raw signal. Next one is by using these large foil electrodes. They were attached onto the outer surface of the shirt. You can be seen the photo. And they were positioned onto the shoulders, sides of the body, and back side of the thorax, not on the front side. Two different electrode placement configurations were used. First one was covering the trunk vertically, and second one covering it horizontally. And results show that the respiratory activity is available in the cases of both configurations. The cardiac activity can be assumed to be available in the case of first configuration, the highest excitation frequency, black line. Secondly, with the same electrodes, but directed to follow the cardiac activity. So they were positioned on the upper arms and the chest to get access to the subclavian arteries and veins, and to the heart. And it can be seen that the respiratory activity is available, but cardiac activity cannot be recognized with full certainty. And finally, the textile electrodes. Single configuration was used to cover the full trunk, and the electrodes were connected by using conductive thread. And can be seen that cardiac respiratory activity is available. The cardiac activity can be assumed to be available in the case of highest excitation frequency, the black line also. To follow the measured waveforms in the same, measured on the same frequency, this kind of graphs were created, and it can be concluded that cardiac activity is not available in the case of the three chosen lower frequency setups, but it can be assumed that it is available in the case of this 20 megahertz excitation frequency. And in the case of 10 megahertz, the amplitude is about twice lower than in the case of other setups. So the numerical evaluation reveals that the highest amplitude of signal is gathered in the case of this electrode shirt number 1, where the large surface plate electrodes of foil contact surface were used. And in the case of 5 megahertz, the highest value achieved. In the case of contact electrodes, it's more than 4 times lower when compared to this ES1 result. Now, concerning the cardiac activity, it can be assumed that the filtering can reveal more data. So this is here is the raw signal, and now here is bandpass filtered, post-filtered later in lab view, which incongruously gathered ECG signal. Typically, the human heart beats 60 to 100 beats per minute, and 12 to 18 breaths per minute. So this makes about 5 to 8 heartbeats per 1 cardiac cycle. So it is so available here as well in this count. And concerning the spectral analyze, to see if we can follow the cardiac activity also in this method, the fundamental signal of respiratory activity is clearly available. So this is in logarithmic scale and this is not. but the cardiac activity cannot be recognized from the noise. So this spectral analysis does not support the assumption that it's visually available. So to conclude, the design of the wearable device has enormous effect to the result of the measurements of vital signs. The respiratory activity can be assumed to be available from all of the experimented excitation frequencies and configurations. The cardiac activity seems to be visually available in the case of highest excitation frequency, but nevertheless the spectral analysis does not support this, and the analysis and processing of the signal can reveal interesting data concerning the cardiac activity especially. So a bit about the current work and the future status. We are focusing onto the complex solution as the motion artifact, which we are not considering in this study, has enormous effect. So we are planning to add the coils, for example, into this integration into the clothing or garment elements, to have another method following the vital signs, or following the distance between the coil or the electrode and the body surface. And the future work is to redesign the device, bind the complex device, incorporate into the clothing, and also make cooperation with competence in textile design. Thank you. Here are my contact details. So, any questions? Can send me as well.
Thank you very much. Of time for a couple of questions. Please. Have you been considering other techniques for those parameters measurement? Because I was amazed, and even one of my students was excited, and he did the investigation. There is a technique when the measurement of the breath and heart rate and even the saturation of blood is based just on simple video. By looking into correlation between frame to frame into tiny differences, you can tell the breath, the heart rate, and etc. etc. Or you can take the photoplatismogram. If it is red and infrared, you have one information. If it is red and green, you have another information, and so on and so on. Have you looked into other techniques?
Thank you for the question. Yes, photoplatismograph typically presumes the device that is attached onto you somewhere. Yeah. We are aiming to the device that is incorporated in some kind of clothing element, which is hanging freely on you. Well, typically, the sportsmen maybe have these tight-fitting shirts and pants. We are aiming to some regular shirt that you can put on and it is unnoticeable. And yes, video is another option, very widely investigated, but the same issue. To integrate it into the clothing. So what we have tried is magnetic induction. So I mean the coils, single coil solution. It's another possibility to integrate into the clothing.
Okay, so the answer is no. You
no.
Did not.
We have tried this magnetic induction. That is
okay,
the
but
other
you
method.
did not look into
But not the ones that you were saying.
Then another question comes from this. It is good that you are trying to devise some parameter which will indicate the quality of what you are getting. But don't you think that noise also has to be included? Because you are measuring just the amplitude. You are missing the amplitude, I can increase the amplitude.
In this case, yes. This is the initial study of this prototype of the device, and that was the way how we evaluated the availability of these vital signs that we are interested in. This is the current
But if the signal noise ratio is high, I can increase the amplitude as much as you want.
Yeah, yeah.
And I will spoil you. My proposal is to use signal noise.
Yeah, I agree, and thank you for this comment.
question? Just one. Did you actually measure the electrical impedance of the body? Because this was on your title. Do you have a measurement of the impedance of the body?
We measured the output voltage. We did not calculate the impedance.
Okay. So you don't know how much the impedance is changing?
No, in numerical value, no. Yeah, we didn't do the calculation.
Did you consider that you can get some kind of information from
Yeah,
that?
yeah. This should be definitely included if the device is.
If you are even throwing away the imaginary part,
yeah.
maybe this can be.
Yeah.
Okay. This was our last speaker, and now the session is finished. So thank you all for coming, and thank you to the speakers, and thank you to the audience for the questions, and we can